don't need a clock to get to the clear signal and do some assessment. The only way that you can make the clear synchronous is to get by the clock and just the clock. And only C does that. Then in the always loop itself, then you would have it if clear equals 1, do whatever you're going to do. Yes?
So would B not do it?
No, because what happens if I don't get a clock but the clear signal gets asserted? Then it would be asynchronous because I wouldn't need the clock. Yeah.
Can we also go over number 2?
Number 2.
Still fairly confused about the RTL.
That was corrected on the test. The answer is no, because RTL coding is behavioral or data flow. And that's why some of you will have a pen grade on there rather than the normal printout, because when I had put together that the master slide that gets run through the machine first, I had the wrong answer on there. And that's why if you look on D2L, it says updated, because I had to change the answer to 2 to no. Anything else?
If we have any that are correct, and we just checked and it's still marked them wrong, should we just come see you?
Okay, if you believe the machine corrected that, did the correction, graded it wrong, what you need to do is at the break, circle the question
Okay.
and give me your stance on it.
Okay.
And I'll take a look at it. Some people did not erase too well, and machine doesn't like that.
You go to 3 is all.
3, consider the following partial program. Okay, so I have an OR gate where the output's Y and the input is A and B. And A is equal to the AND of B and C. Whoops. And then R is equal to the exclusive OR of Y and C. So that's what the circuit looks like. So if you look at this, this is B and C exclusive ORed with B. Well, here's B and C, it's not exclusive ORed with C. So this one's out. A or B or C is equal to R. That's not true. And then finally you have B and C, so this is A or B. Exclusive ORed with C. That's not equal to Y. Because Y is A or B. So that one is. So it's none of the above. Anything else? Which one? 14. 14. So this is the exclusive OR reduction. So starting from the right-hand side, 0 exclusive OR 1 is a 1, exclusive OR with 0 is a 1, exclusive OR with a 1 is 0. So that would be A. Because starting from the right, you exclusive OR bitwise and work your way all the way through to the most significant bit. Anything else?
So this is like valid syntax, right? Because I was confused and I put the caret on, like, I thought, it's like you self XOR it with self or something.
No, that's the reduction operator for
yeah.
exclusive OR. There's also a reduction operator for AND and OR and so on.
Because in C you can, like, you put the caret on, like, Y caret on it.
This is valid syntax.
Yeah.
Use 7.
7. Oh, great. Wow, this bled through. Okay, so these are blocking assignments. So if you look at that, you start out with A is a logic 1. At 10 time units, it goes to a 0. At 20 time units, so this would be a 30, it's still a 0. At 42, it's still a 0. At 57, I'm doing this adding right, it's a 1. At 79, it's still a 1. And then at 109, it goes to the 0. So it asked, how many times did it go from logic 1 to logic 0 twice? At 10 and at 109. I'm sorry?
Those are relative delays because they're blocking something.
Correct.
Okay.
If they were non-blocking,
Then they would have the arrow.
that you'd be recording the, well, it actually would give you the same thing with non-blocking. Because all this does is record the right-hand side. And then at the end, it generates that waveform. If these pound sign delays were on the right-hand side of the equation, then those become absolute. And you get. We're going to be talking a little bit in this lecture on blocking versus non-blocking assignments. A couple times. No que plus. Anything else? Okay.
Yeah, one more, 12. So you're saying instantiation creates an object in a module, but in your actual slide, you say it's creating a module from a template. What's up with that?
This was how we actually defined instantiation, was creating an object in a module. The object that you create was defined by a module template that would be external to the module in which the instantiation is actually done.
Oh.
Value change dump files, VCD, an acronym I expect you to know. All right, so let's suppose that you want to debug your design. And let's talk initially about a C program. So a brute force way of doing it is at certain places in your code, you could put printf statements, and that would display on standard out the value of various variables at various times in the execution of your program. A more efficient way of doing this well, maybe I can spell it. A more efficient way of analyzing your code to see what's going on is with something called a source level debugger. Anybody know what a source level debugger is? Okay.
It will, I assume it will like step with your code and show you like line by line debugging.
Okay. It allows you to monitor certain variables. It allows you to set breakpoints in your code where your code can execute at normal speed to the breakpoint. At the breakpoint, then you could print out a variable, all variables, whatever. And that's a much more effective way of, and efficient way of doing debugging is with a source level debugger. Now, in Verilog, we don't have printf statements, we have that display statement, which is equivalent to the printf in C. We also have that monitor statement that you only need to put once in your code, and anytime any of the variables changes, it'll do a printout. But there is an equivalent type of source level debugger in Verilog, and it's the value change dump files. And there are a series of system tasks that support this value change dump file. Should define this formally. A value change dump file is an ASCII file that stores timestamped signal changes. And we're going to take a look at one of those shortly. It turns out that you could figure out by reading this value change dump file what actually transpired in your design when you did the simulation. And you can actually, and this is typically done with post-processing design automation tools, they can take the value change dump file and actually create the timing diagram showing you when signals changed, what the stimulus was, and so forth. And that's what some of these design automation tools do. And we'll take a look at one of these shortly. So when it comes to actually doing the debugging and analysis, this is what takes place. You do your design simulation, and by putting some system tasks in there, which we'll take a look at shortly, it will generate the value change dump file for you. And then design automation tools can then look at that. They'll know what signals changed, what they changed to, and what time, because it's timestamped. And then they can do analysis and debug and so forth. And then you make whatever design changes you need to based on those results and resimulate. So this is the loop that you would go through to functionally check out your design. Once the design is functionally checked out, then you can go on to the next phase, which would be the synthesis phase. So this example 915 shows some of the system tasks that are associated with creating this value change dump file. And these system tasks are, like other system tasks, embedded in an initial or an always loop. Usually an initial loop. So in this initial loop, this system task $dump file defines what my value change dump file name is. And the name is enclosed in double quotes. So here I'm calling it myfile.dmp. So then if I have dump vares, this one, there are no arguments, it dumps all the signals in the design. Now it may turn out that you don't want to necessarily dump all of the signals to see what's changing in the entire design, because we've talked a little bit about design hierarchies, and I may have multiple levels. And if you look at all the possible signals in all the modules, there may be too many of them. So dump vares would dump everything that you have. You may be interested in just dumping a portion of the design, maybe just the signals in a particular module, maybe just a signal in a module. So some of these other commands, when dump vares with arguments, allows you to do that. So here I have dump vares 1 comma top. Top is assumed to be the top level of your design hierarchy. That will be your test bench. And as it says, is the number 1 indicates the level of the hierarchy. This says to dump 1 level below top. So all this would do would just create a value change dump file that shows the signal transitions timestamp in your test bench, just in the module top. Now here it's assumed that in the design hierarchy, in top I have, if I go down 1 level, a module M1. So this is implying about this sort of thing. Here's top, and one of the modules I have instantiated in that is M1. So if I have dump 2 comma top dot M1, it dumps up to 2 levels in the hierarchy below top M1. So what that does is it will show in the value change dump file any signal changes in top and any signal changes in M1. Now I may have other modules here, those will not appear in the value change dump file. If you do 0 comma top M1, you dump the entire hierarchy below M1. So that would do top and M1 and any modules that are instantiated in M1. So by changing the arguments, you can specify exactly what timestamp signal change you want in the value change dump file. So in this initial statement, I have dump on, that starts the dump process, and pound sign 100,000 dump off. So this would start at time 0 and start doing your dump. However, you've defined, like up here, what you want actually dumped. So if I had, let's say, pound sign 1000 dump on, it would wait until time step 1000, and then it would start doing the dumping. And then at 100,000, it would turn it off. Yeah.
So the dump there, when you do the 1 comma top, basically, if I understand this correctly, it just dumps the variables in top. And then if you go down to the second one where you do dump var var 1 comma top, or I'm sorry, 2 comma top M1, it dumps the variables in top and M1 for that.
Right, if I had, here, dump vares 1 comma top M1, it would only dump the signals in M1. But by putting in the 0, it says I want these as well. So you can control what you want. And then you can create a checkpoint where here I would dump all of the variables. Now, those are the ones that were described in the text. There are a number of other commands that are not specified in your text. So I'll cover those briefly. As you can imagine, if you have a rather involved simulation, that file is going to grow, because every time you get a signal change, you get a new entry in the value changed on file. And that file can grow and grow and grow and grow and grow. And you may have a limited amount of space that you can, that you've set aside for that dump file. So this system task will limit the size of the file that you've specified. Don't forget the terminating semicolon. In this version here, and this 0 is required, these may just be specific signal names that I want dumped. And what this would do then is just take these particular variables and put those in the value change dump file. Give you an example here. In this particular module div, I've got a signal.clk, I've got a signal CLK, and so all I want to appear in the value change dump file is that particular signal in that particular module. So you don't have to dump all of the signal changes in a module, you can just pick certain signals and have those appear in the value change dump file, yeah.
For the dump limit, when you reach the limit, what happens to the file? Does it override it or just
No, you get a simulator warning.
warning?
In fact, no, you probably get a singular simulator error because you've overwritten the file. And I'm going to show you how quickly that value change dump file can grow. Okay, so those are a couple of other system tasks that you can use. So I took a design that I simulated, and what I did was I implemented a D flip-flop, and I'm going to look at 3 different commands to show you what changes. So here's what a value change dump file looks like. And I've shown you the, down here, the timing diagram for my simulation. Okay, first of all, I hate this, and I gotta leave that on. Okay. Okay, so in this particular case, my top level module was test, and GG is the name of the D flip-flop I instantiated. These are signals from the module template, and those were the corresponding signals that I declared in the test bench. Okay? Now you'll notice that there is a symbol here associated with each one of those signals. A left open paren is for the Q output on my module I'm instantiating. The ampersand is for the clear signal. The D input in the test bench has got a, what is that, a pound sign, and so on. So there's some character associated with each one of the signals in the test bench and in the module I instantiated. So now, here's what I've done. Now, these are time stamped. So this says at time 0 are the signal with the left open paren, which is what? That's the Q output in my instantiated module. Everybody see that? And it has a value of 0. What's the tick mark associated with? Which signal? What?
Clock.
Clock input, where? In the test bench or in the instantiated module? Where?
Looks like it's the instantiated module. It's under module, what does it say, GG?
Yeah?
And then it's the third one, wire, clock.
Yeah, it's the clock signal in my instantiated module. What's ampersand?
Is that the clear in the module?
That's the clear in the module, that's a 0. What's this one here?
Yeah, pound sign.
It's a what?
Pound sign?
Yeah, but what signal is that
Oh.
associated with?
It's D? Yeah. D is
In the test bench or the instantiated module?
test bench.
In the test bench. These tell me the initial conditions of all the signals in the test bench and in my instantiated module. Does everybody see that? Okay. So now, this is time stamped. And the units here are nanoseconds. So at, well, this is 5,000 time units, that's 5 nanoseconds. 2 signals went to logic 1. The clock in the test bench, and since that spoke to the clock in the instantiated module, they both go to 1 at 5 nanoseconds. At 6 nanoseconds, 2 signals change to 1. Which ones are those?
Clock in the test bench and block in the module?
No,
No, I think it's clear.
clear. The, is that an asterisk or a double quote, one of the two? I don't have my glasses, so I can't see. That would be at 6 nanoseconds, that would be the clear, and that's hooked to the clear in the module. Now, let's take a look at the timing diagram. There's the initial conditions. It looks like at 5 nanoseconds, CLK goes to a 1. At 6 nanoseconds, clear goes to a 1. This is an ASCII representation of the transitions that you see in this particular timing diagram. It's timestamped. By using these symbols, this will tell me at this particular time what signals changed. Does everybody see that? Okay, now. This value change dump file that you see was based on this particular system task. And I said that what I want is my test bench, which I call test. And the 0 says dump the entire hierarchy. So that's what you get. Now you see how long this file is. It's not that long of a simulation time, it's only 60 nanoseconds. But see how long the file is? That's because I was dumping everything. Here, same thing, but I have a 1, so I limited it to just the test bench signals. And see how much shorter the file is. So I'm not dumping everything. So you can see how changing this affects the length of the value change dump file. So you could actually, and no, I'm not going to require you to do this. You could actually take a value change dump file and reconstruct that. And that's what design automation tools would do. And you can specify by using the appropriate arguments here, just specific signals that you want to look at, just specific modules that you want to look at, and so forth. And then using the dump on and dump off commands, you can specify just certain time periods that you want to see what went on. Okay. So that's the value, no pun intended, of the value change dump files. Okay, so now let's move on to synthesis. And we'll formally define this as the process of creating, I should say converting, a high-level description into an optimized and I'm going to put this in quotes, gate level net list. So, and we've seen this before, I I've got the three inputs. Some hardware description language, a library of components, and a constraint file. And what I get out here is a optimized gate level net list. Okay, so I need to explain a couple of terms there. I had mentioned this before. The term gate level net list has kind of just been adopted. It's true you will have a gate level net list if we're talking about synthesizing my design into an ASIC. However, if I'm going to do this in an FPGA, and we're going to be looking shortly at some of the internal architecture of FPGAs, there ain't any gates in there. So the term gate level net list, even though it's commonly a adopted term, does not really apply if you're dealing with FPGAs. But we'll see how the architecture of the FPGA is used to implement your hardware description language description of your circuit. Term optimized. This particular tool has a number of options. We're going to be looking at a user's guide for a synthesizer. And there's a number of switches or options that you can choose to get your design efficiently implemented either in an ASIC or an FPGA. So that's what the term optimized applies to. So at this particular point, this hardware description language has already gone through that debugging design that we showed before, where you wind up with a functionally correct design. You believe that it is functionally correct. Then and only then would you actually go to the synthesizer, get your gate level net list, and then from there you'll go through placement and routing, you'll do your timing analysis and so forth. And we'll get into some of that a little bit later. Some notes. What you're actually synthesizing is RTL code. Normally, your design will be RTL coding, which means that your description of your circuit is done either in data flow and or behavior level. We'll get into some situations on when you may want to use gate level abstraction, but normally it's RTL code that you synthesize. The design constraints will include things like pin assignments. If you're doing an FPGA as your target device, the pins have to be assigned. And so those are one thing that will go in the timing constraints. But the thing that definitely has to be there are your timing constraints. Those are absolutely essential because if you do not put any timing constraints into that user constraint file, then the synthesizer assumes that you don't really care about timing. And what you can wind up with is a inefficient layout. And you may have a design that doesn't work at the speed that you actually require, what's specified in the design specification. So this is always included in your constraint file. A little bit later on in the course, we're going to be looking at timing constraints, and we're going to see the type of timing constraints that Xilinx typically specifies for their FPGA-based designs. So this is figure 14-2. And this shows the synthesis process. Your architectural description here is some sort of design specification. And from that design specification, you will do your high-level description, your Verilog code. And then you go into the synthesizer. There will be some optimization that takes place based primarily on options that you've selected for the synthesizer tool. And then a check will be made to see whether or not you meet your constraints. If you've not met the constraints, what do? Go back to the high-level description. Now, I'm going to add this as well with a dashed line. Let's suppose that you haven't met a particular timing constraint. That may not necessarily require that you make any coding changes. In some cases, what you may do is go back and re-synthesize the design, choosing a different option. For example, I may have a finite state machine in there, and I have told the synthesizer, I want you to use full encoding. And maybe you don't meet a timing constraint. You may want to go back and say, well, let's re-synthesize it, but let me change that option to where the finite state machine is one hot encoding. And let's see if that has any effect on satisfying that timing constraint. In most cases, you're going to wind up going there, but in some cases, you may try different options on your synthesizer without making any coding changes and see if that makes a difference. So I'm going to add that little arrow in there. And I'm putting it in dashed lines because sometimes that may be worthwhile, sometimes it may not, in which case your only recourse is to do some recoding. Once you've met all of your constraints, then you go on to place and route. And I'll talk a little bit about that in this course, but effectively, the course ends there. Portland State does have a series of courses that deal with placement and routing, but those are graduate level courses. They're not undergraduate courses. When you look at the synthesizer user's guide, and this is something I had mentioned before, you will find a table that tells you any restrictions on your coding. And before you attempt synthesis, you need to look for that table and verify that the code that you've written hasn't violated any of these restrictions. So this is a hypothetical logic synthesizer. It says that it will support input, in-out, and output ports. What are in-out ports?
Bidirectional.
Bidirectional ports. It'll handle parameter statements, modules. The only declarations it will handle are wire declarations, reg, and tri-state. You can instantiate modules and gate primitives. It will handle functions and tasks, but notice that any timing constraints that you have are ignored. Those pound sign delays, for example. Under procedural, it'll handle always, if, then, else, case X, and case Z. Initial is not supported. Always procedures are supported by synthesis. Initial are not, and that's typical. Under procedural blocks, it'll handle begin and end, named blocks, disable. Under data flow, it will handle the continuous assignment statement, but again, delay information is ignored. For loops, it'll handle for, while, forever. And it tells you that while and forever loops must have some sort of synchronization associated with them. So your always statement, for example, has to have the positive edge of a clock or the or something like that. Observations. We've said this many times that all timing delays are ignored. So as a consequence, you may find that your simulation results quite often will not match your synthesized results. I can put pound sign delays in my code and I can simulate it. And I'll get my timing diagram and everything will be fine. But since the synthesizer ignores those timing delays, your synthesized result is not going to produce the same result. So that's one of the reasons why you don't want to put any of those pound sign delays in your module templates. It's fine to put them in your test bench, but you don't simulate test benches. You simulate design, you synthesize designs, not test benches. The initial procedure is not synthesizable. No synthesizer supports that. I said before that the simulation results do not match quite often your synthesized results. This one might be surprising. Your synthesized results may not give you what you want. It may be a successful synthesis, but the design is not what you want. Now, I'm not talking here about timing violations. It may actually satisfy any timing constraints that you put in. If you said this design has to work at 200 megahertz, it may work at 200 megahertz. But the synthesized results may not be what you want because it depends on how you coded the design. Or put another way, syntax does matter. I'm going to be talking a little bit about synthesis for ASIC design. And what I'm going to do then is show you several different instances of different types of syntax we've discussed, and show you the type of circuitry that would be synthesized if we're doing a gate level design. And some of this may surprise you as far as what you get. And you can see how if you're not careful with your syntax, you may not get what you wanted. So syntax does matter. This is example 14-4. And this is sometimes referred to as the design flow. It's the design steps that you need to go through. You start out with a RTL description, and then this goes through some translation. And what you get is an optimized intermediate representation, and then you'll go through some logic optimization and then technology mapping and optimization. Now this stuff that's here in this dash box is pretty much hidden from you. You don't get involved in any of that. These are requirements and functions done by some of the design automation tools. I do want to make a comment on the logic optimization. You would think that turning on logic optimization would be a good thing. Some of you may have had experience in writing C code where there were different compiler options, optimization levels, and it would change your code before it created the executable file. Well, the same thing occurs here, but you have to be careful. One of the logic optimizations it's done is to look for and eliminate unnecessary code, unnecessary descriptions. Well, here's an example of how logic optimization can come back to haunt you. If you are doing a combinational logic design, you may have looked for hazard conditions. And you may have put in a hazard cover into your design. That hazard cover is not required to implement the Boolean equation. It's to prevent glitches. The logic optimizer may say, well, that hazard cover isn't needed, doesn't contribute anything to implementing the Boolean equation. And so it removes it for you, but that's not what you want. So if you're going to use some optimization level in the synthesizer, make sure you understand what that's going to do to your design. This technology mapping and optimization, what they're talking about there is taking your design constraints and your library and mapping it into a particular device or set of devices. And then what you get out is your optimized gate level networks. Okay? So, let's take a 10-minute break, and when we come back, I want to take you through and show you some aspects of synthesis of ASICs. Is James Sheridan in here? Is Matthew in here, who we have an appointment? I'll leave this.
How'd you do, Aaron? Yeah. He said I missed 4, but the Scantron marked it wrong, so I only missed 2.
Is there any
I can do it 3 more.
Okay, then why don't we do this?
Do you remember which number he said was wrong again?
What was that?
He said one of them. What was the question about the RLC? RTL.
RTL, that was number 2.
Okay.
So what I can do is,
Yeah, your 2 is actually wrong.
Yeah. Did I really want to figure it out?
Yeah, I had to think about that one, but you had to make sure that you notice it said gate level included in it, which isn't included.
Really exotic experience. No. If I'm from Vietnam, I would speak Vietnamese to him. I wouldn't speak English to him. Okay, do you know? Yeah. Okay, do you speak? Yeah. You do? Yeah. No way. You do? How much do you
That's just me not sleeping. Well, it's the intonation. There's five, there's rising, falling, up and down, down, up, There's up, flat, high, low.
Keep getting the old pointer when I'm trying to get old pointer.
My next couple weeks, we guys have
I keep getting the old
I'm trying to find myself.
Nothing works out.
It's like, yeah.
Oh, what am
It's also an easy one here, but there's some, they don't really use prepositions, they're, they don't look to.
It's really hard to.
Well, and for me, let's say that, right, so, I'm like, so here, based on the track stuff, like, you have like three classes after that, but then, depending on what vowel, it's the next one, the vowel that is written in kind of, like, together, this consonant can either be here, here, or here. And so like reading and writing, it's just kind of confusing. But that has for some reason, you have to do homework most of the time because you
So with Faust is
Jim was a lot more
You're still like, no, we should have some pictures for each word. This is very bad. Well, this will give you like.
Yeah, I mean, it's very
This is why he's going to actually.
Keith Laundry was more like he had to do.
Big Jack is not there. Yes, you found a library.
So you only have to be there for like a year and a half.
I took that. Yes. That was
You were.
You write it.
Yeah, it was just a nice, sounding voice. Like the time we wanted,
Okay, this library right here, available gates, leaf level cells, the technology library as it's sometimes referred to. When we're talking about FPGAs, that's what you will find in the technology library. For ASICs, it contains something called standard cells. And each standard cell is going to contain the following information. Obviously, it'll have functional information. For example, I'll have a standard cell, it's a 3-input AND gate, so it'll have the function. It'll tell you a little bit about how much area is going to be occupied when you put that on the silicon, when you instantiate one of those cells. You're also going to get timing information. And power consumption. So when you buy a standard cell, the vendor who's selling you that standard cell is going to provide you with all of this information. This functional info and the layout are going to be used by the synthesizer to determine where to place the cell on the silicon, and obviously the functional information will be to choose the appropriate cell for whatever function you're trying to implement. The architecture of a standard cell design looks like this. You're going to have a series of rows here, and some of these blocks will represent a standard cell. And you'll notice that they're not all necessarily the same size, which you would expect. If I've got a 2-input AND gate, intuitively that would require less room than, say, I don't know, an 8-input OR gate. So these are of different sizes. These will show interconnections between different standard cells. Some of these blocks will not represent standard cells, but an actual spacing called a via, V-I-A, and that will allow a cell in this row to connect to a cell in that row. And so you can route that connection through this gap, if you will, in this particular row. So this is the architectural layout for a standard cell type of design. So to give you some sort of an appreciation on what's involved in doing an ASIC design, I want to look at an example. And the example I'm going to look at is a magnitude comparator. So I'm going to have two 4-bit inputs, let's say A and B, and I'm going to have 3 outputs, And obviously, only one of those outputs is gonna be asserted, depending on whether A is greater than B, less than B, or equal to B. And I'm assuming that A and B are unsigned integers. Okay. I'm gonna want the propagation delay, TPD, to be as small as possible. Now, you have to be careful here because area and speed tend to be mutually exclusive. They tend to be reciprocals of each other. And that's shown in this figure 14-5. Where along the ordinate here I have the area of the design on the silicon, and along the abscissa I have the associated propagation delay. And as you allow more area for the design, you cut down the propagation delay. So high speed implies that you're going to use large area. The reason why is because one of the ways that you get high speed is to do different portions of the design in parallel. If I'm doing stuff in parallel, I've got additional circuitry to support the parallelism. And so that's going to require more area. Yes?
I'm sorry, did you say the larger the area of your design, the lower timing delay is gonna be?
Yeah, the lower the speed.
Doesn't the speed of light become an issue as your designs take up more die area?
I'm sorry, say that again?
Doesn't the speed of light become an issue when your designs take up larger area?
Well, our designs that we have aren't operating close to the speed of light.
I mean, but if you have a chip that's approaching hundreds of megahertz or gigahertz, then the largest die.
All right, let me give you an example of what I mean. Does anybody know what carry look-ahead circuitry is? Do you? Did you raise your hand? Anybody here? All right, what's carry look-ahead circuitry?
It's where they do some, because there's a propagation delay through the adding circuit, so you can add some extra logic that looks ahead and it skips the exact thing, and just checks to see if there's gonna be carry out.
Precisely. I've got an adder circuit and I'm building it up with a bunch of cascaded full adders. When I apply two numbers to be added, the carry out of the least significant bit has to carry over into, no pun intended, into the next most significant bit. That has to propagate into the next one, and so on. And so your carry has to propagate through all of the bits, and that cuts down the propagation delay, or that increases the propagation delay of the adder. What carry look-ahead circuitry does is it figures out which bit positions will have carries without actually doing the addition. And so then you just take the number A added to the number B plus a vector of carries in the individual bit positions, which were calculated by the carry look-ahead circuitry. You get a much, much faster addition with that. That carry look-ahead circuitry requires that you give up some area to implement it. So if you want a faster full adder, you need to implement carry look-ahead circuitry, you gotta consume more area for that additional circuitry. And there's an example of, I'm gonna let you use some more area, but I'm gonna get a faster circuit. Yeah.
So, but like nowadays CPUs are getting smaller and faster. That's I think what he means.
Yeah, there's still, it's regardless. I don't care if you shrink the design in half, you may get faster propagation delay, or a lower propagation delay, but it's still not what you want. to get what you want, you may have to implement something like carry look-ahead circuitry for the given area that's been allotted to get the design to work. Okay. So that's what they mean by the trade-off between the area and propagation delay. All right, so my design that I want to look at is this magnitude comparator. And so here's the code, RTL description for my magnitude comparator. I think this is one that we've seen before. Module and module. There are my 3 outputs, there's my 2 inputs. The 2 data inputs are 4 bits, and I have a single bit output. And then I use a continuous assignment statement to assign the outputs. And these are relational operators, so they're going to return a value of 0 or 1. Obviously, only one of those is going to be a logic 1 for any given input A and B. So there's my design. And as it says here, it's very concise. So, we have this fictitious ASIC vendor called the ABC 100 Technology Company. And they say, we will provide you standard cells as follows. And here's their names and there's their functions. This is very limited. They're only going to provide a 2-input NAND gate, AND gate, NOR gate, OR gate, an inverter, a buffer, a negative edge triggered, and a positive edge triggered D flip-flop. That's all they sell. You can actually build up any logic device with just those components, because you recall that any combinational logic circuit, for example, can be built solely out of 2-input NAND gates or 2-input NOR gates. So that is sufficient to build any design you want. So we've gone to the ABC 100 Technology Company and we said, show us what you got in your standard cell library. And they said, that's what we offer, that's what we'll sell. So here's the test bench for our magnitude comparator. We're going to define some reg variables A and B, and they're going to be the outputs. We instantiate our module that we had just taken a look at. We've now connected up by position my test bench signals with the signals defined in the module template. We have an initial statement, we have a monitor. This function here, $time, this is a timestamp function system task. Now you recall that anytime any of these signals changes, A, B, A greater than B, A less than B, A equal to B, this monitor statement will print this on standard out. By putting this function in here, it will print out the time that signal changed and the values of all of those variables. Okay, so that's a very useful system task for keeping track of simulation time. So then I've got these test cases. This obviously is not an exhaustive test, but I've got 1, 2, 3, 4, 5, 6 test cases that we're going to use to evaluate the capabilities of our design. This figure right here, this is figure 14-6. Shows how that design would actually be implemented. We've gone through the synthesizer, and you use the technology library from the ABC 100 Technology Company. This is the circuit that would be synthesized to create that magnitude comparative design. You'll notice that it's comprised of devices that the ABC 100 Technology Company provides. There's 2 input OR gates, NAND gates, there's an inverter, and so on. Okay, so the ABC 100 Technology Company has provided devices that I can use to build up that design. So here is what the gate level description would look like coming out of the synthesizer. And you'll see here that it's written in a kind of like a Verilog code. There are the devices that it used out of the ABC 100 Technology Library, and this has the standard gate level description syntax that we're used to in Verilog, where the first entry is the output and any remaining entries are the inputs. This wire declaration up here is for defining the internal nets. I've got an internal net, for example, there. It's not connected to one of the inputs or one of the outputs, so I have to give it a designator so that the interconnection between the gates can be hooked up. So that's what the synthesizer output would look like. So let's suppose that I want to synthesize this design. This is a gate level description of the design in terms of the ABC models. See any problem with trying to simulate this? Let's suppose that you wrote this. There's your schematic. You start picking out VNANDs and VORs and components out of the component library, and you wrote this gate level description, and you want to simulate it. Any problems that you can foresee?
Trying to interpret the simulation to see if you even simulated the correct design.
Now let's assume that the test bench that I showed you, that was adequate. You want to run that through QuestaSim or ModelSim or any other simulator. See any problems?
There's nothing about timing. There's nothing about timing for each of them.
But we don't worry about timing in simulation, right? What's a VNAND gate?
It's a type of NAND gate.
Think the simulator would understand that? The simulator would understand NAND because that's a defined gate primitive in Verilog. VNAND is not. These are names from the ABC 100 Technology Company. Verilog doesn't know what a VNAND is, or a VOR, or VNOT, has no idea what those are, so can't simulate it. So it turns out that the ABC Technology Company is going to have to provide to you a simulation library. And here's what their simulation library will look like. First of all, this is standard Verilog code. Module and module. This happens to be for the V and out, N0, N1, and these are declared okay. Now let me skip this for the moment. Look what gets instantiated. A standard AND gate defined in terms of a gate primitive any Verilog simulator will understand. AND. So there's the function. Now, if you want to do some timing information, it also would provide timing information. I find this of dubious value. Nevertheless, it is there. This shows from the input N0 to the output and from the input N1 to the output, the rise time and the fall time. And there's 3 values there separated with colons, giving you minimum, typical, and maximum propagation delay from the input to the output. First of all, they took that out to 6 significant figures, which I don't know if you need that kind of precision. The typical value should never be used because you always do a worst case timing analysis. So the only value of any use here is actually the maximum. But you should not rely on your simulator to do timing analysis. You should do timing analysis on a synthesized design. But the point I wanted to bring up, specify here is the fact that when you do your gate level description, using standard cells provided by a ASIC vendor, you have to use their names so that when it gets synthesized, it will be synthesized correctly. But for simulation purposes, you need to rely on a simulation library from the vendor so that you can actually simulate your gate level description. And so they need to provide you this as well. Okay, so now I want to talk a little bit about managing complexity. And what I'm talking about now is a thought process you need to go through before you create your design hierarchy, identify the modules, what gets instantiated into what, and before you write your first line of code. This is a thought process you need to go through to manage the complexity of the design. So these are some guidelines for managing complexity. You do these before coding. So these are just some guidelines. First, I'm going to define some terms here. The data path. This is your collection of ALUs, arithmetic logic units, registers, logic blocks. And buses. Essentially, your data path is anything that's going to be actually manipulating data and the devices that are going to be used. Any devices that manipulate data fall into your data path. Control path. This is any sequencing logic that controls what happens on the data path. For example, let's suppose I've got an arithmetic logic unit on my data path. That arithmetic logic unit is going to have a binary input that defines what function you want that ALU to do. Is it doing a multiply? Is it doing a subtraction? What is it doing? Those command and control signals that would be fed to the ALU to define its function, those come off of the control path. And the sequencing logic, and I'll show you a couple of ways of doing that, is the circuitry that provides those command and control signals. So you've got a data path where you're processing data, and you've got a control path that provides the necessary command, controls, status signals, and so forth that determines what happens on the data path. So your first guideline is to clearly separate the control path from the data path. Incidentally, none of this is in your text. As a matter of fact, we're now done with the textbook. So you don't need to bring the Palatnikar book to class anymore. We will, however, be looking at a lot of stuff that I already have or will be posting on D2L. So if you're going to follow along, you need to bring some sort of PDF reader of some sort. It's not going to be feasible to print out the stuff. You can if you want to, but some of the documents that we're going to be looking at are hundreds of pages long, and might be easier to use some sort of PDF reader. Okay. Guideline number 2. Structure the data path. And what I mean by that is determine what functional units adders, multiplexers, etc. are needed. So you're going to have to go to the design spec, find out what your design is supposed to do, And then you structure your data path by figuring out ahead of time, what kind of functional units am I going to need? This is where you do design trade-offs. There's more than one way to implement a design. Different design approaches may use different functional units. That's where you would start to do this particular analysis. Figuring out how you're going to process the data that you're going to have to deal with. There may be multiple ways of doing it. This is where you start looking at, okay, here's the functional units, here's how they would be connected together. Effectively, you're doing a block diagram of functional units to show how data is going to be flowing through and gets processed from input to output. So that's where you will do your design trade-off. Okay, once you've structured the data path, you want to identify all control points. These are points where the control path and data path intersect. Effectively, what you're doing is, once you have structured your data path, you now can figure out what kind of command and control signals am I going to need to actually get data to move through this data path and do all the necessary processing. Effectively, what you're doing here in this, when you identify all the control points, is you are identifying all of the command and control signals that are going to be part of your control path. Now, once you have your control points identified, you determine a control strategy. So I'm going to have to generate a series of command and control signals that need to be defined. Not only are they supposed to be logic 1 or logic 0, but at what time should these command and control signals be asserted to get data to flow through the data path. So when I talk about a control strategy, what I'm talking about is different ways in which you can generate these command and control signals that you're going to need to get data to move down through the data path. So one of the ways you could do it is with some sort of counter. So here's my counter. Here's the clock. And the end bit output of the counter goes into some decode logic. Which will generate M control signals. This is next state logic. And I'm gonna take a feedback from here. And let's say I have L bits of status input from the data path. This next state logic would determine whether this counter is supposed to increment on the next clock, or maybe it's supposed to be loaded with some other value. This next state logic would look at the current value, output from the counter, and based on status information it's getting from the data path, you may modify that count. And then the count goes through decode logic that generates your control signals. So that's one form of sequencing logic. Another way that you could do this is with finite state machines. And this is quite frequently used as a method of implementing a control strategy, because you can go from state to state to state to state, and in the finite state machine state diagram, you recall that there are inputs that determine which state transitions you take. And that input information would be status input from the data path. So that was guideline 4. Guideline 5. Determine a reset strategy for your design. Quite often you have designs where certain devices must be initialized. Some initialize to logic 0, some to logic 1. In some cases you may initialize it to a value. For example, I may have a counter that's initialized to some value other than all zeros. So you need to determine which devices what initial values and recall that some devices are synchronously initialized and some are asynchronously initialized. And then the most important step which I'll define as my first law. Design before coding. Before you sit down, you have your hands poised above that keyboard, ready to start writing those modules, you need to back up and start applying some of the guidelines we've just talked about. Design before coding. Figure out what your design is supposed to look like. determine the control path, the data path, figure out some way of generating those command and control signals that you're going to need, develop a reset strategy, and then you should be ready to start writing that code. See you Thursday.